Okay, good morning. We have the recording going. Today we're going to be reviewing Chapter 7, Electrical Systems. We'll be mixing in some Chapter 10, Troubleshooting Diagnostics. We'll be talking about how to read spark plugs, and we'll be doing some electrical system testing as well. So we got lots to cover, lots to do. So with that, we're going to go ahead and get started doing it. So I'm jumping in our Chapter 7 material. And with that, we're going to start right here at the basics. Whenever you're dealing with electricity, it's good to know how, what's going on in there and how it all comes together. And to really understand that, you have to go down to the electrons. I see a lot of problems with electrical diagnosis, and I'll have students coming to me and they ask, oh, I don't have power here, or I'm looking for juice. And I know if somebody tells me they're looking for juice, they're already off in left field. They've missed the boat. They don't really understand what's going on here. So to get that good electrical understanding, you really have to start down at the atomic level, looking at electrons, and then from there we're going to move to conductors and insulators and everything else. Okay, so what do we have here on the screen? Well, we have a copper atom here. And then if we look on the outside of the atom, there's all these electrons orbiting around like moons orbiting around a planet, right? And really, electricity is the movement of these electrons from atom to atom to atom. So electricity is the movement of electrons. Now, with copper is a very good conductor. So if we look at copper wire, we had some wires and they had some black plastic insulation on them, let's say. So here's our insulation. But coming out of that insulation, we had our copper wire. Copper is a very good conductor. Why is it a good conductor? Well, because in its outermost electron ring, also called the valence electron ring, it only has one electron hanging out there. And that means that electron, he doesn't have any buddies there for support. He's loosely held. So copper is a good conductor because it's very easy to take this outermost electron and skip him or move him from atom to atom to atom. So it's a good conductor. It all comes down to the atomic level on how tightly held are its electrons in the valence or outermost electron ring. So items that are good conductors, copper, steel, aluminum, they don't have a lot of electrons in that outermost ring. Now, how many could you have? Well, you could pack in 8 electrons. And so if I started adding, there's another one, there's another one. Boy, they're not real good looking here, but you get the idea. So I'm gonna pack this up with 8 there. So I got 3, 4, 5, 6, 7, 8. Let's try that again. 1, 6, 7, 8. Now I'm getting 9. All right, but you get the idea. If I had 8 electrons there, that would be an insulator, because having 8 electrons there, they all kind of help each other out and they're tightly held and they don't want to give up that outermost electron. So an insulator, a material like rubber or glass or most of your plastics, those have a lot of electrons in the outermost ring, and that means that they're not willing to give up their electron very easily at all, and so they resist the flow of electricity. So you can see that like on a piece of copper wire, for instance, we wrap it in a rubber plastic insulation on the outside to keep that wire from shorting out and keep those electrons moving through the wire and not touching other things and flowing other paths, right? So it all comes down to the atomic level. How many electrons are in that outermost electron ring determines if you're a conductor or an insulator, and electricity itself is all about the flow of electrons. I got one curveball for you. What about a semiconductor? Well, a semiconductor would have exactly 4, so I'm drawing those in green, or trying to, 4 electrons in its outermost electron ring. And that means that that semiconductor, think of like a computer chip or a transistor or a diode, like we're going to talk about here in a minute. That means that those items can either act like a conductor and let electricity move through them, or they can act like an insulator and stop electricity moving through them. So a semiconductor almost can act very easily like a switch, an on-off switch, where it lets electricity through and then it stops it. So it would have 4 electrons in its outermost electron ring. Okay, so with that, let's keep moving. So here we have in the picture, we have a picture of a starting circuit or cranking circuit that's used to crank over the engine so we don't have to pull the pull starter, right? And we're doing some voltage measurements with a digital multimeter. Sometimes these are called DMMs for digital multimeter. Other times they're called DVOMs for digital volt ohm meter. In any case, this electrical multimeter, we have some of those pictured here, and they're measuring voltage. And so what is voltage then? Well, voltage is electrical pressure. And it says it's measured in the circuit, and it's the difference between 2 points. And so you can see, like, if they're measuring between the negative battery terminal here and the positive battery terminal there, like this particular meter is, he's measuring basically what's the battery voltage. So he's going between the negative battery terminal and the positive battery terminal, and he's measuring 12.6 volts, which, by the way, for a standard, what we call a 12.6 volt or a 12 volt battery, it's 12.6 is actually 100% charged. So I'm trying to draw 100 there. So anyways, we think it's a 12 volt battery. If it's actually sitting at 12 volts when you measure it, it's actually at 50% state of charge. So, so we're doing a voltage measurement, but what technically is voltage? Voltage is electrical pressure. So the more voltage you have, the more pressure you have to make things happen. So for example, I could take my 2 hands and I could grab onto the 2 battery posts. So if I'll change that to a different color, and here's my hands, and here's my stick figure guy. Not looking real good, but you get the idea. I could touch those 2 battery posts and it's not going to shock me because it's only 12 volts, and 12 volts is not enough electrical pressure to force any electricity through my body. However, if I stuck my fingers in a light socket, right? Oops, there we go. If I put my 2 fingers in that light socket, well, that's 120 volts or 110. That is enough electrical pressure to do quite a bit of damage and force some electricity through my body. So the easiest way to think of voltage is think of it as electrical pressure, and we commonly relate electricity to water. So here I'm drawing a big water tower here, and think of this as being your water in the water tower, right? The more voltage you have, the more pressure you have, water pressure, if you will, trying to get that electricity to move through a circuit. Now, it's not the voltage that does the work in the circuit, it's actually the flow. But if I don't have any voltage, if I don't have any pressure, right, I'm not going to get any flow. So I need to have voltage there. Now, you might be wondering, well, how do I get how do I get voltage there? If I cleared all these drawings and I went back a slide, back to these atoms, if I took some atoms here and I'm going to draw a barrier here between the atoms. And the ones on this side, I basically, I took away their electron. Well, electrons have a negative charge. So I took the electrons away. And so now these guys have a positive charge. Now, what did I do with those electrons? I took those electrons and I stacked them over here on these other guys. So these other atoms have some extra electrons, which again have a negative charge. That's why these are all showing little minus signs there. So over here on this side, we have a more negative charge. So inside a battery, there's a series of plates made out of, in most automotive batteries, they use lead, so made of sponge lead and lead peroxide, that basically on one plate, we stack a bunch of positive ions or positively charged atoms. On the other plate, we stack a bunch of negatively charged ions or negative charged atoms. And that's how we charge the battery up. We're stacking extra electrons on the negative side. When you have that difference between the positive side and the negative side, that's your difference in voltage. That's your voltage potential there. That makes your electrical pressure. So again, it all goes back to the atomic level. All right, well, usually my students start fading out on me when I start talking about atoms and stuff. Just remember that voltage is electrical pressure. And without voltage, we're not going to get any flow in the circuit, so nothing else is going to happen, right? If your car won't start and you don't measure 12.6 volts there, right? If your battery is dead, it's game over, right? So always start with the basics. All right, so moving right along. I beat you up about what's voltage. Now we're moving on to current. So what's current? Well, current is the actual flow. So current is the flow of electrons through the circuit. So if I don't have any voltage, right, if I don't have any pressure, I'm not going to have any flow, right? If I didn't have any water pressure, I wouldn't have water flowing to my house when I opened up the faucet, right? So I have to have pressure to get the flow. Current in electricity is our actual flow, and it's actually what does the work for us. So it's actually the electrons moving in the circuit, right? So for instance, in your book, and in that case on the test and everything, it'll talk about how if you have 1 volt, that will push 1 amp of current through a circuit that has a resistance of 1 ohm. And it would take 1 amp to push, or 1 volt to push 1 amp in a circuit that has a resistance value of 1 ohm. That's kind of the basics of Ohm's law. But what I'm getting to here is if I don't have any voltage, I'm not going to have any current. The current is what actually does the work. So if I look at this picture over here, what you'll see is you have an AC voltage source and a DC voltage source. Let's start with the DC. DC stands for, if I can get my text tool going, DC stands for direct current. And what does that mean? That means that current flows in one direction only. In this case, if we think about it truly, it really does flow from the negative to the positive, because that's where all the electrons are stacked up, right? It's always going to flow from an abundance of electrons to an absence. But we typically think in what they call conventional current flow theory, which we think it flows from positive to negative. It doesn't really do that, but honestly, it doesn't really matter which way the current's flowing. The key is that it flows in one direction. Now, if we look at this schematic symbol for the battery, this is a little wiring schematic, notice that they drew the battery as a series of positive and negative plates. That's what a battery is, right? And in this case, the load is whatever device you're trying to operate, whether it's an ignition coil or a light bulb or a motor or whatever. In this case, the load looks like it's a light bulb. So electricity flows from negative to positive. The current is flowing through the filament of the light bulb. So that causes the filament to glow and produce light, and it goes back to the other side of the battery. And then as those electrons move from one side of the battery and get to the other side of the battery then discharges, right? So that's direct current. That's relatively easy to understand. But there is also, if I switch it back to my text tool here, alternating current, or AC. That alternating current, or AC there, it basically flows back and forth, back and forth. Now, there are some spots on our small engines where we use AC, but the most common place where you're gonna find alternating current is in your house. AC works better to ship electricity over long distances because you're not having all the electrons move one direction. Like you see in the screen here, what we're doing is we're going back and forth. Remember, it's the current that does the work in the circuit. So this light bulb doesn't really care which direction the current goes. If it's moving back and forth through the light bulb filament, the light bulb's going to turn on and glow. Okay, so it's just the movement, the flow of electrons. It doesn't matter if it's flowing back and forth or all flowing one direction. Well, if you're trying to ship power hundreds of miles or even a few miles from the power station to your house, AC, alternating current, works much better for that than DC. So that's why your house uses DC. But inside your house all the time, if I reach on my desktop here, oops, where'd it go? Maybe I put it away. All the time, you have inverters. Well, I was looking for my cell phone charger, which I must have put away. But here's an example. This is a rectifier or a little power box, right? You would have similar ones for your cell phones and stuff. That's because your cell phone uses a battery. So your cell phone is DC. The nature of a battery is it uses direct current, right? So you have to have a little box here like this that converts the AC from your house into DC to charge up your cell phone. Any device that you have that uses a little box like this, that's what they're doing. They're taking the AC and converting it into DC. So now we know about what current is. It's the actual flow of electrons. That's what really does the work in our circuit. And it can either come in two flavors, two varieties: alternating current, where it's moving back and forth, or direct current. By the way, in your house, it moves back and forth at a frequency of 60 hertz. So that means 60 times per second, it's moving back and forth. All right. So with that, we know about voltage, electrical pressure. We know the current is the flow of electrons. And now we're going to look at resistance. And so what they've shown us here is some different sizes of copper wire, right? And it is interesting to note that on the American wire gauge system, as the numbers get smaller, right, 12, the wire gets bigger. So like a battery cable is going to be like a 2-gauge wire, maybe a 1-gauge wire. a 22 gauge wire is something really small that might do your dome light or something, right? So you get the idea. The bigger the number, the smaller the wire. Okay, but what's the deal with this? Well, see this symbol right here? Ohms divided by 1,000 at 68 degrees Fahrenheit. So what they're relating to is that, hey, every component has a certain amount of resistance. So I'm going to actually type that in, resistance. So what's resistance? Well, it's the opposition to current flow. What's it measured in? It's measured in ohms. So if I change my colors here and we think about electricity again being like water, right? And here is my water hose. And so here's my green water hose here. And yep, I got some water flowing through the hose, pouring out on the ground, right? Well, what's resistance? Resistance then would be a kink in the hose. So if I got a pinch here in the hose, guess what? That's going to oppose the flow. Does it oppose the water pressure? No, not really. The pressure can still build, but as soon as you open up the hose and it starts flowing, then you're going to see a pressure drop across this kink, and it's definitely going to impact the flow, right? So what is resistance? Well, resistance is a kink in the hose. It's opposition to the flow of current. So the more current I'm trying to flow through a wire, the more resistance the more resistance I could encounter, especially if the wire was smaller, right? So the smaller wire, it would limit my current flow. So every conductor, I don't care how good the conductor is, it's going to have a certain amount of resistance. And every component you're trying to operate has a certain amount of resistance as well. And they all oppose the current flow a little bit. So those three entities work together in electrical circuit, right? Voltage, current, and resistance. So notice nowhere in this these examples have I talked about juice, because there is no juice in there. There's voltage, there's current, there's resistance. If you're looking for juice, you're looking for a bottle of OJ at your breakfast table or something. It's not in the electrical circuit. Okay, now some of you are probably thinking, well, what about watts? Like my house is billed in kilowatt hours. Well, you probably don't think about that unless you're paying a power bill at your house. And if you're like me, you went, oh my goodness, that cost a lot more money last month. And they charged me in kilowatt hours. So what are watts? Well, watts or wattage is a measurement of power. Now, electrical power is if I take the voltage and I multiply that by the current, that is going to equal my power or my watts. So in the case of a home, when you're trying to measure, well, how much power has this house consumed, it makes sense to take the voltage and multiply it by the current, and that's how much wattage you consumed, right? If you're looking at an electric car, or even let's say an electric blower or something, and they talk about, oh, it's X amount of watts or whatever, right? Well, because watts is a measurement of power, it's more powerful if it's you got more watts in there, right? Because that means your motor is going to consume more voltage and current. It is going to run down the battery quicker, by the way, but it will, you know, push more air in the case of a blower. If it's a car, that means it's going to go faster. You get the idea. So voltage is electrical pressure. Current is the flow of electrons through the circuit, and resistance, like you see on the screen right here, is a kink in the hose or opposition to that flow. Wattage is a measurement of power, and that's you taking the voltage and multiplying it by the current. Our electrical multimeters, they don't actually measure watts, right? But they can measure volts, and they can measure current flow or amps. Current is measured in amps. So they can measure the current and they can measure the voltage, and then you can multiply them together if you wanted to figure out what the watts are. Anyways, so no juice, voltage, current, resistance. That's your first step to diagnosing electrical problems. So knowing what you're talking about. Okay, this slide takes us kind of back to where we were before. When we were talking about AC or DC. If you've ever seen maybe on TV a scientist using a machine, or you know, sometimes you see it in old movies, or used to see it on the ITT technical college advertisement, but you'll see a machine and it's displaying this sine wave, this image here. Well, this is a sine wave. And because my voltage goes in this direction for a minute and then that direction, that's going to cause the current flow to go this way. And then it gets over here and it says, oh, I got to go the other way, right? So that's one AC cycle. So this is called an AC sine wave. And it's what, if you graphed out the voltage, what's actually happening in the circuit as the electricity goes back and forth, back and forth, back and forth. So this is an AC sine wave. And again, here they're counting the cycles and the time, and they say, hey, we have a frequency of 5 hertz. In your house, we have a frequency of 60 hertz going on. In fact, so many things use that frequency, it's pretty tightly kept. So for instance, a clock, an electric clock in your house is more than likely, especially if it's a digital clock, it's going to count the 60 cycles every second, and that's how it measures its seconds in time. So, all right. So AC sine waves, that's what's going on there. DC would look like a flat line. AC's a sine wave back and forth. All right. Can we convert AC to DC? Yes, we can. And that's why I was holding up this little power box, right? This converts the AC to DC. This one says its output is 12 volts at 1.5 amps, if I read the back of it. So the AC, this is, you plug it into the wall, that's what's going on in your wall. And then the electronics inside the box, the transistors and diodes, will basically, what will be coming out of it will look something like that, which will be a kind of a pulsating DC, but good enough to charge up your device. So that's what's going on there. Now, how does it relate to our engines? Well, if we have, let's say, a riding tractor, a riding lawnmower, that's going to have a 12-volt battery on it. So I have to charge up that battery. Well, a battery, as we talked about before, a battery is a 12-volt, or not necessarily 12 volts, but a battery is a DC device. It's a DC animal, if you will. So batteries are only compatible with DC. Well, my charging circuit actually charges AC because that's more efficient, and that's just kind of the way it works. It charges AC, and then we have to convert the AC from our charging system to DC. So if you've heard of an alternator on your car, oh, I need to replace my alternator. Why do they call it an alternator? Because inside of it, it produces alternating current, or AC. That AC gets rectified to DC before it leaves the alternator, And that's what you're seeing here on the screen here is AC being rectified to DC. And it's, you know, it's fun history. If we had more time, and you can study up on it, but if you're into electrical circuits and stuff, if you look back, Thomas Edison, Nikolai Tesla, Tesla was a big AC guy. Edison was a DC guy. He didn't like AC, so whenever you converted AC back to DC, you rectified it, you made it correct. And if you made DC into AC, you inverted it, you made it incorrect, right? So anyways, one path for current to flow in a series circuit. So what we're talking about now is series circuits and different circuit types. So a series circuit, I have, just like it shows, one path here for current to flow. Notice that they're showing the current flow in conventional current flow theory. The switch has to be closed. So when you turn a switch on, you're closing the switch, allowing electricity to flow through it. Both these lights turn on, and then it flows back to the battery. If the switch was opened up, or if this light bulb burned out, both light bulbs would turn off, because there's only one path for current to flow. So your really, really old Christmas lights were series circuits. If one light bulb burned out, the whole strand would go dead, right? Modern Christmas lights are really modified from this, because you can have a light bulb fail and the strand keeps going. If you unplug a light, though, commonly, the strand will die, or at least a part of the strand will die. Because modern Christmas lights aren't series, but I'll write down here that the old Christmas lights, that's a good example of a series circuit that we can all relate to. Okay. A parallel circuit has more than one path for current to flow. So an easy way to think about this one would be the headlights of your car, right? So current's flowing through there. I could have one headlight fail, the other headlight keeps working. Okay, they're not in series. One headlight fails, the other one keeps working, it's parallel. So if this light burns out, this one stays going. So that's a parallel circuit. Now, there's also what we call, if I can get it up here, is series parallel circuits, where we have a combination of some parts of the circuit in series, some parts of the circuit in parallel. And you can see that here on the slide where I got these two lights. If one of those lights were to fail, back up just a bit. If one of those lights were to fail, the other light would go out, right? But this light that's in parallel would keep working. Well, now you're probably wondering, just like I did, is, well, how do these new Christmas lights work then? So here's my Christmas light strand. There's the bulb socket. Here's another bulb socket. And here's another one. Well, we know in those bulb sockets, there's different bulbs, right? I'll have a blue one, a red one, and I don't know, maybe an orange one here, because I like colored Christmas lights, but I digress here. All right, so inside each light bulb, you have your filament, which I'm trying to draw there, but you also have a little parallel path, which I'll draw down there, that has a resistor in there. So what happens with the new Christmas lights is they are a series parallel circuit. All the bulb sockets and all the bulbs themselves are in series, especially on the shorter strands. They're in series, but actually in each light bulb is a mini parallel circuit. There's two pathways in each bulb. So the bulb can burn out, the strand keeps going because it has that parallel path inside of it. But if I were to take the bulb out, the strand goes dead, because now I've removed both those circuits. So now I've broken it, and I'm down to just the series part of the strand. So anyways, pretty pretty ingenious how they fix that. Series parallel circuit. So we got 3 circuit varieties or circuit flavors. We got series, we have parallel, and then we have a combination of the 2, series parallel. All right. On a small engine, you're likely to see, or a vehicle for that matter, you're likely to see a combination of all 3 depending upon what these circuits go to power. Or you might have your control, here the switch is in series, but everything else that it controls is in parallel. So a good example of this would be the lights on the dash of your car, right? You turn on your headlights, all your little instrument gauges glow in your car. If you have a new car, it's all computer screens and stuff, right? But if you have an older car, like mine, it's got gauges and they have little lights on them to backlight the gauges, right? Well, all those little light bulbs are in parallel. So if one fails, the other ones keep working. But the switch that controls those lights is in series. So oftentimes our circuit will have the controls in series and all the devices in parallel. Or, I'll clear this out, I'm going to draw another electrical schematic symbol, if I can. This is going to look like a wavy line, almost like a sine wave. But this is the electrical symbol for a fuse. So the fuse will be in series, but all the circuits that fuse protects are in parallel. So you might have a fuse that goes to your cigarette lighter and your dome light and your radio. All 3 of those things are in parallel, but that one fuse is in series. So if the fuse is removed, all those things basically turn off. They don't receive any voltage, therefore they're not going to have any current flow and they're not going to work. Okay, moving right along. Here's some different diagrams, right? From exploded view diagrams to here is a kind of a wiring diagram that has more than just the electrical schematic symbols. It's actually got some components. It's nice when you have those. And you can see like how that starting circuit's wired up in the charging system. This slide, I'm going to skip it pretty quickly because we've talked about how electricity and magnetism are related. I can use magnetism to make electricity and vice versa. And how our ignition coils use laminated stacks to increase the effects of the magnetic fields. So this is for a charging circuit, but you can see laminated stacks in there. So here's what I wanted to say is that we commonly think of like the magnets in our flywheel going past in exciting our ignition coil. But if I have, let's say, again, I'll use that riding lawnmower example, it's got headlights on it. Usually it's got a battery. Some of those really nice ones have radios and all kinds of stuff on them these days, cup holders. I don't know where you're going on that thing. But anyways, they have all these accessories. So they need a charging system to charge the battery. So what do? On the inside of the flywheel on the small engine, they put a series of magnets. And these magnets then rotate around this stator assembly, and that stator produces an AC sine wave, which gets rectified to DC. It goes through a little metal box thing. And some of you guys will see, you might get the Briggs electrical test, because remember they kind of randomize the questions, but you might get the test where there's like a little box with some wires coming out of it, and it looks like a little silver metal box with wires, and it says, what is this little box thing? Well, that's your voltage regulator. That thing actually helps convert the AC back to DC, and it regulates how much output this charging system is going to have. So inside a small engine, you don't have a big alternator mounted there. What you do have is extra magnets inside your flywheel and a stator assembly underneath all that stuff that acts as your charging system. Okay, so moving right along then. Here's an example of that charging system working, and they have half wave versus full wave rectification. It kind of depends on how much output they want out of the alternator on a small engine. They might have enough output with half wave rectification, or they might need more output, so they'll make it full wave. The small engine manufacturers, like all manufacturers, are very cost conscious, so they know what the electrical demands are, and they build a charging system that just meets those demands and not extra. So car manufacturers are the same way, and it's probably a better example because people will put all kinds of modifications to their car, right? Big stereo system, all this stuff, and then they wonder, well, why does my battery keep going dead? Well, they might have placed so much extra electrical load on their car now that the charging system, the alternator, can't keep up with it because it wasn't built for that, because putting an alternator that could put out more amps would cost more money. So you might have to upgrade that charging system if you're putting a lot of extra stuff on there. Okay, so here is a couple examples of different systems. Again, if I take my drawing tool, see this little metal box? Okay, that's your regulator and rectifier assembly. So what does it do? It converts the AC and it makes it into DC, and it regulates the output. So this one that puts out more amps, a 16 amp output system, has the bigger metal box there with multiple wires. The 5 amp to 9 amp system has a smaller metal box, and this would do half wave rectification where this does full wave. Anyways, you get the idea. They're gonna choose the one that meets the needs of that particular make and model. We're getting a full wave rectification. I don't need to like bore you with this stuff. It's just using all the pulsations coming off the alternator. Here we have a diode bridge or Wheatstone bridge being used. So we use diodes here. This is a Zener diode. Diodes are semiconductors, and that means they can conduct electricity 1 minute and not conduct it the other minute. See how these all have like an arrow on them? These diodes let electricity flow through them in the direction of the arrow, but not in the direction against that direction. So what's really popular these days are flashlights and stuff, but these flashlights use light emitting diodes. These are diodes that if you put the battery in this thing backwards, it's not going to work because the electricity has to flow through it one direction only to make that diode turn on and illuminate. Kind of a fun thing, where if you took your regular light bulb type flashlight, if you put the battery in wrong, it would work. Okay, this is battery condition is checked using a hydrometer. I would say not so much anymore. Most battery manufacturers don't want you to open up the battery and suck the acid out, because if you get any contamination in the battery, it ruins it. So battery condition is usually tested with a battery tester these days, or a voltmeter. Remember, a fully charged 12-volt battery should have 12.6 volts on it. All right, moving right along. Don't overlook the basics. Corrosion at the battery terminals is going to create all types of problems and headaches. That corrosion at the battery terminal is essentially a lot of resistance. It's going to oppose the flow, and it's going to make stuff operate all weird. So I've had cars that wouldn't even start up and run, and people brought them in there, oh, I think it's the computer or the starter went bad or what, and it's corroded battery terminals. Start with the basics, fix those things, and move from there. When you're doing diagnostics, that's always the best way to go. We've talked about the flywheel magnets, like that one would be one for an ignition coil. And now we're getting back to spark plugs. So if we relate this back to our ignition system, remember that we are trying to get the electricity to jump this gap in the spark plug, right? We're trying to get this electricity to jump between the ground electrode, or from the center electrode to the ground electrode. And electricity doesn't like to jump gaps. In fact, electricity, remember, it's much like water. It's going to take the path of least resistance. So if it's easier for it to leak out of the spark plug wire and ground out to the engine metal, that's what it's going to do. Okay, so it takes several thousand volts, in the neighborhood of somewhere around 5,000 volts, to get electricity to jump the gap of the spark plug inside our engine. So what we have to do in our ignition coil is we have to take whatever voltage is developed from the flywheel, from the magnets on the flywheel, that magneto, we got to boost that voltage up to 5, 10, maybe 15,000 volts to get the electricity to jump the gap. Now, if it's too hard, if it's going to take 20,000 volts to jump the gap, and this coil is only capable of producing 15,000 volts, guess what? It won't jump the gap and the engine's not going to start, right? So things like the spark plug gap is super important, because if the gap is too big, here it says the gap, and the gap for a stock Briggs and Stratton engine is 30 thousandths. Well, let's say I, messed up and I set the gap to 50 thousandths, 0.050. Well, it's not going to be able to jump that gap. My engine's not going to start. Let's say I set the gap to, I don't know, 0, no gap. I dropped the spark plug on the ground, and when I did that, now the ground electrode's touching the center electrode. This happens quite a bit, really. So I dropped the spark plug, it's touching the ground electrode. Well, guess what? I'm not going to get a spark down because it doesn't take anything for the electricity to flow from one to the other. So I have no spark. I'm not going to create any heat, because the whole reason I'm making the spark inside the combustion chamber is to make heat to get the air-fuel mixture burning, so I go on to the power stroke, right? So if I don't have a spark, I don't have heat, I'm not going to burn the air-fuel mixture, and my engine's not going to run. So is your spark plug gap important? By all means, yes, it is. The preferred spark plug gapper are these wire style ones, because you can use them even on a spark plug that's a little bit worn, and you get the idea. Now, let me back up one minute. Speaking about these spark plugs, electricity likes to jump between nice sharp edges. The edges of the electrode will wear off, round off over time, because you have several thousand volts jumping a gap in there. It arcs, right? That's what the spark is. And as that spark or arc occurs, it does wear away the metal of the electrodes, and the electrodes slowly get more and more rounded, and the gap gets bigger and bigger and bigger. And so it takes more and more voltage to fire the spark plug as the plug becomes worn. And you can get to the point where the spark plug's so worn, it can't jump the gap anymore, and now the car starts running poorly, or the engine starts running poorly. So that's why you're supposed to change your spark plugs, because they do wear from electricity jumping that gap between the center electrode and the ground electrode. Okay, we'll get back to reading spark plugs here in a little bit. How do we fire the coil in the spark plug? Well, last week we looked at our still presentation, and they had some pretty fancy ignition modules built into their coils. Before that, though, what you had was breaker points. Breaker points were just that. They would open up in the electrical circuit. So if I can get it on the screen, these points would open up, and that stops the flow through the primary. It makes the magnetic field collapse across the secondary, and that's what makes the spark plug fire. So older engines in the Briggs and Stratton world, this would be pre-1982, they used breaker points. But newer engines will use electronic ignition systems. And in the Briggs and Stratton world, they call it the magnetron. In fact, I'll just go to the next slide. So breaker point actually had points in there. And so on an old car, like when you were doing what they call a tune-up, you would replace spark plugs and wires. You would replace the breaker points. You would also replace this little box right here that they've drawn. That's the condenser. All those things were parts of a tune-up to make the engine run well. And oftentimes, if you did that tune-up, the engine ran better because those parts commonly wore. And and they would change when the spark plug fired, right? So the downside of breaker points is as the points mechanically wear down, and they do mechanically wear down, it changes when the spark fires in the 4-stroke cycle. So it changes your ignition timing, and that's going to change the way that the engine runs. So in the car world in the 1970s, they realized that, oh, when the points wear, the ignition timing changes. And you know what that changes? That changes the emissions at the tailpipe. So again, our emission regulations helped bring us a much better ignition system that moved away from breaker points. That took a few more years in the small engine world, but by the later 70s on through the early 80s, we moved away from breaker points and went to electronic ignition. Okay, so there's just a wiring schematic of the breaker points and how the condenser works. When the breaker points open, that's when the spark plug fires. To keep the breaker points from arcing up really fast and getting ruined very quickly, you have a condenser there that acts as a little battery that can be charged up to prevent arcing across the points. We replaced all this mess of stuff here with what they call the magnetron, okay? Think of magnetron is your electronic ignition system. Magnetron is just Briggs and Stratton's name for it. So what did they do? Well, they replaced that with a trigger coil assembly, which essentially consisted of a transistor and a trigger coil in there. And in the later ones, it's all black plastic molded together so you can't even see what's in there. But essentially, this coil is like your ignition coil and your ignition module all wrapped up into one. So if I clear out my drawings and I keep this presentation moving, I want to show you some slides because you will get questions on these. I stole these off of one of the Briggs videos or something. So your basic magnetron ignition system, you can see that the air gap here is filled. There's not much gap. It's small, right? That's your conventional magnetron ignition system. Small gap there. However, there's a downside to that. Now, what's inside that magnetron ignition? It's got your secondary winding, your primary winding, and your transistor right here, and your trigger coil assembly. Those take the place of your points, right? The downside of this system, and I'll get to this here in a second, is that it doesn't advance the ignition timing the faster the engine rotates. The ignition timing actually retards a little bit as the engine is running faster. And so from a performance standpoint, it's not the best. So remember that the conventional magnetron, although it's good because it got rid of points, it's got the small gap there. It's not necessarily the best for performance. For performance, they have an advancing style and it's got a bigger air gap there. So if you got the bigger air gap, it's got the ability to advance the timing. It's more like the still ignition coil where it's got more electronics in the coil, in the module to make it work. So anyways, big gap, it's got advance on it. Small gap, it doesn't do advance. This would give you more performance. So like if you dyno tested your engine with the conventional magnetron and then you put this one on and re-dyno tested it, this would make more power. But it costs more money to produce. So if it's a lawnmower, who cares, right? But if it's something that's more high performance, maybe it's a riding lawnmower or just a more expensive piece of equipment, well, then they're likely to use the advancing style. Let me back up to these slides a little bit. So to replace the points, we use a trigger coil and we use a transistor In this case, they're calling it a Darlington transistor because it's got actually a pair of transistors. It's called a Darlington pair. It's got this pair of transistors in there that basically act as the on-off switch. So remember I said earlier, semiconductors, they can flow electricity or they can not. That's what we use to make transistors and diodes. And so in this case, those transistors, they can flow electricity 1 second and the next split second stop the flow of electricity. So it's like having an electrical switch, like in the points, it's like having that switch, but there's no mechanics here to wear. So how electronics tend to work and then how they tend to fail is they work and work and work and work and work, and then one day they just don't work. Or they work and work and work and work, and they start getting kind of heat sensitive. So they get real hot and they start puttering out and quit working. You let them cool off again, they start working again, and then if you kept driving it that way, eventually it would quit working. Points, over time, they degrade and degrade and degrade into the point where it quits working, but in that process, it started running poorer and poorer and poorer as these mechanically wore down, where electronic devices are more like they work and then they don't work, or they work and become heat sensitive and then they don't work. Mechanical things wear, electronic components are more like here and then they're not there. Okay, so we talked about the gap. Remember, the advancing has the big gap, the non-advancing has the small gap, and how that interacts with the magnets on the flywheel, and how the magnetron got rid of the points, replaced it with a trigger coil and a transistor assembly. So we've answered some test questions there for you. This is talking about just the ignition timing. Remember the whole concept with ignition timing, as the engine is rotating faster and faster and faster, more and more RPM, there's less time there to burn the air-fuel mixture. So ideally, you want to get the spark to the spark plug sooner and sooner and sooner, okay? So you might have on a car 30 plus degrees advance at high RPM. So there's the advancing style. You can see there's a lot more electronics inside there. What's funny is in this diagram, they even give us the champion spark plug number. Remember that plug number relates to the heat range and everything else. Type of electrode, all that stuff. Okay, advancing style has the big gap. Sometimes they have a purple band on them. Not always though. Look for the gap. You got a gap, it's the fancy coil that can give you spark advance. Oh, cranking speed. They talk about 350 RPM from the old ones, but now, this is a test question for you. Now you need 250 RPM to get some spark out of this thing. So what does that mean? If you don't have enough muscle to pull the rope fast enough, it's not going to make good spark. You got to pull that thing hard and fast enough so that the motor actually clears 250 RPM. At that point, this thing can start making some spark and working. You're not collapsing the magnetic field fast enough if you're pulling it over really, really slow. So I've had some people say, oh, my engine's hard to start. And I go to work on it and I'm like, this thing starts fine. And then I had to say, oh, show me how you start it. And I realized that they can barely pull the rope over. Well, you're not moving it fast enough. So, all right. 250 RPM. Keeping stuff moving. Here's some slides on the starting system. Of course, a starting system is separate. The ignition system fires the spark plug, right? The starting system cranks over the engine, and that keeps you from having to pull a pull starter, right? I think because people in their car, you have an ignition switch, or older cars had an ignition switch. Now, new cars have push buttons and stuff, but you know, people will get the ignition system and the starting or cranking system confused. The starting system is there to crank over the engine. The ignition system is there to fire the spark plug. So this stuff would be just like a starting system on a car for the most part. You're gonna have to have a 12-volt battery, all that type of stuff. If you have a riding lawnmower, they have an ignition kill wired up to the seat, which sometimes is really irritating, but it's there for safety. So if you get out of the seat, It grounds up the spark and shuts the engine off. Demo board's just that ignition switch, mower blade attachments. All right, we need to talk a little bit about electrical multimeters or digital multimeters, DMMs, and it talks about a continuity test function and truth tables and stuff. So what we're gonna do is do some different tests with our multimeter. Now, let me label some stuff here on this particular meter diagram. Volts, oops, volts AC. Then I got volts, try that again, volts DC. Up here we got our milli, or a small amount of volts. Up here we're going to say resistance. And over here we're going to say current. See if I can move that guy over a little bit. Current or amps. So what we're going to do is look at the different meter positions. So if I was going to use this multimeter to test electricity on my house, I would go to this position where it is right now and be measuring voltage in AC. But if I was testing my car, or most of the stuff on my small engine for that matter, I'd be measuring voltage in DC. So voltage DC has the straight line over it because it's going in one direction. If I wanted to measure just a little tiny bit of voltage, my meter would be more accurate if I selected the millivolt scale. If I wanted to measure the resistance of something or its ohms, I would select the Greek omega symbol, and that is my ohm measurement. Remember, ohms is a measurement of resistance, so that's opposition to current flow in the circuit. And then if I wanted to measure the flow of the circuit, I would have to select one of these ones that has the A there. The A is for amps, and then I can measure the flow of the circuit, okay? You'll also notice that I would have to move my meter leads to these other locations. I actually have to wire up my meter in series with the circuit to measure amps. So of the two most common measurements you do, it's much more common to measure volts and ohms. So that's what we're gonna do up here with the document camera. But let me switch my screen share real quick and just go to the internet, because what I wanted to show you guys was, you know what, you can get a little multimeter pretty inexpensively. In fact, oftentimes you can get a coupon for getting this meter for free, or for like $3 or something like that. This is a great little multimeter. I have one in my truck, and then my wife took my truck this morning, so I didn't have this meter to bring in, so that's why I'm showing you this picture. But it's just a good little meter to have. Would I want to test my house electrical system with it? I don't feel real good about that, because the insulation on these wires is not great, and just the whole thing is, you know, not very expensive. So I don't know if I trust it at 120 volts, but measuring, if I selected this selection right here, that would be 0 to 20 volts DC. I would trust it for that, and it works pretty darn good. So it's not auto ranging. So with the nicer meter, I could just select volts and it would automatically range it. So it could range it for 10 volts, or it could range it for 100 volts automatically. This meter, I have to select the right range. So for working on a car, that's the range I would want most of the time, because it's a 12-volt battery. So that's between 0 and 20 volts. That range will work. This multimeter will allow you to do a lot of tests, and it's a good one to have. So I can measure voltage. I can also measure my resistance, again, it's not auto-ranging, so I have to figure out like, well, how much resistance do I expect to have there? For things that have low amount of resistance, I'm gonna go down to 200 ohms. Something that has more resistance, like a secondary winding of an ignition coil, I might be up here at 20,000. This thing even has a thing where you could use it to test transistors directly, which would be helpful if you're like in electronics class. It does have some limited amps measurements, but they're pretty low amounts. Oh no, there's 10 amps right there. So anyways, it can do volts, amps, you know, good tool to have in your toolbox. And if you are like a tool hound and you have a really nice meter, this is a good meter to have as a backup, as a spare in your glove box or something. All right. So with that, I'm now going to change my screen share again, and I'm going to go to my desktop. And now that I'm at my desktop, I'm going to minimize that, and I'm going to get rid of that and that. And you know what I need to do is punch up the chat. So amp, so there's a question in the chat about, well, what is amp a measurement of? Amps are a measurement of current, which is the flow of electricity, right? So amps is measuring the flow, volts are measuring the pressure, and ohms are measuring the resistance. So if I put up my document camera, if I bring up the Elmo here, we should be able to see the craziness that I have on my desktop here. And with that, we'll get our meter up here. If I put him to volts, you can see I got a wavy line and a straight line. So this meter works a little bit differently. This is my favorite meter because I'm a sucker for a color screen, and it's got a color screen. So, all right, I propped that thing up there so we can see it a little bit better. So for this one, if I want to do AC or DC, I got to push this button. So you can see a little AC. Oops, oh, maybe not. Maybe I should tilt. Oh, I got to tilt it the other way. That's what I got to do. And then I will focus this guy. There you go. So when I push the button, now I'm set up to measure AC. Now I'm set up to measure DC. So I got my AC or DC selection. Okay. So it can measure AC, it can measure DC, it can measure ohms. So here's my ohms measurement. Now, if I take my two leads, in this case, I have one lead that has an alligator clip, and the other lead is a pointing lead, and I put them together, I can test the resistance of my leads. And it looks like my leads have 0.05, maybe 0.06 ohms in them. When you're measuring ohms, power is actually coming out from the meter, flowing through the cables and coming back in the other meter. So an ohms test, in my opinion, using your meter to measure ohms like this, it's really good for like a bench test, but it doesn't put out enough amps to really give you a very realistic test, flowing the same amount of electrons through those wires as they would when the engine's running or the circuit's operating. For instance, these leads measure 0.5, 0.6 ohms. If I tested a big old thick battery cable, it would also measure 0.5, 0.6 ohms because it's just not very much current flow to test all those problems. But for bench testing things, it works pretty well. For example, if I'm going to bring up another electrical tool here. This tool is a test light. So this clip normally gets hooked to ground, the negative battery side. And whenever I touch something that has voltage on it or positive, the light bulb here should illuminate. Well, let's say my test light's not working. and I'm trying to figure out what's going on there. Maybe the light bulb's burned out. I could test to see if there's a complete path for electricity to flow in there. What I would do is I would hook up my meter, I'd set it to ohms, and I'm going to measure the resistance of my light bulb. In this case, I do have continuity, and that's the resistance of that light bulb. It is a complete path, so it tells me the bulb is good. But if I were to take this test light apart, and I were to take the light bulb out of there, I can. Been in here a bunch of years, so maybe it doesn't want to come out. Oh, you can see I moved it just enough, and now it says OL, out of limits, because I've opened up the circuit. So the light, it would not work at this point. Now I've sucked the light bulb back in, and you can see it's measuring continuity, so the light bulb should work. I have a complete path for electricity to flow. So this is a test light. Test lights are nice when you just want to do a quick test. And if you want to see if you have electrical power at a point, test lights work really well. But they're not computer safe, so there's areas where it's not safe to use a test light. Obviously, you can see the multimeter gives you a lot more information.
Why do you have 3 leads?
Why do I have 3 leads?
Yeah.
Well, this is from the test light, and then this is my other lead and this is from the multimeter. This is the negative lead off the multimeter going to the other end of the test light. Yours might be seeing, oops, my desk is getting all messed up here. That was an ignition tester. So I really only have 2 leads, but with the test light, it looks kind of confusing.
I get it. Thank you. Because we can only see the top part. We can't see what's connected to what. So I got confused. Right.
Yeah, I just have 2 leads going on right now, but I am going to switch my leads in a minute to do another test. So that's a resistance test of the test light, right? And resistance tests are good for doing what I'll call bench testing of components. Now I got another component here. This is a ignition coil, but this one's off of one of my goat kart engines, and it actually has the ignition module with the trigger coil and transistors and stuff in it in the front. So on the side of the engine, it's got its speed sensing element that hooks up to these 2 terminals here, which then trigger this guy. And then these 2 wires here go to the primary side of the coil. So remember that your ignition coil has 2 windings. He has a primary winding with a couple hundred turns of wire, and he's got a secondary winding with thousands upon thousands of turns of wire, right? So I got my primary and my secondary. Well, I can test these with my meter on this particular coil because all the wires are exposed. On the primary winding, I expect to have low resistance. But on the secondary winding, because there's so many more turns of wire there, fighting the lighting here, because there's so many more turns of wire on the secondary side, I expect to have somewhere between maybe 5 to 15,000 ohms of resistance because there's so many more wires. So I could use my meter set to ohms and kind of test that out. And if the coil, if one of these wires on the inside of this coil that I can't see the wires because it's all epoxied in there, but if one of those wires were broken, I would find that out. I would have it out of limits. So the first thing I'm going to do is I'm going to test the primary. So I'm going to go to the negative lead. That normally screws to the engine. And then I'm going to take my other lead of my multimeter, and I'm going to go right here. And I expect it to have a pretty low reading. I get that together. Maybe I'm making a bad. I get 7, 8, but man, it's a lot. It's pretty high. It's up in the megas, so it's millions. See if I can get something a little better. When you're doing resistance tests, having a good, clean connection is super important. Wait a minute. I missed something. I wasn't looking at this right. There's my negative connection right there. This is just an extra ground. There's my negative connection because it's going to the laminations of the coil. Let's try this again. Well, that didn't help. Maybe this is a bad coil. Maybe there's a reason that it's sitting on my desk. Let's test the secondary side of that circuit. So I'm plugged in there. The secondary, what I'm going to do for him is I've changed the probe on my negative side. I'm going to plug this right into where the spark plug would hook up. This is the one where I expect to have somewhere between 5 to 10,000. Oh, I don't have hardly anything here. So that's probably what's going on with this, is I got a bad coil. Interesting. So I can do ohms tests with this. If I wanted to, well, let me test something else, another electrical component. This little box thing, that's a relay. We use relays all over when we want kind of like an electrical switch, and we don't want to flow a lot of electricity through a switch on our dash. So the relay will have two terminals that have some resistance. In this case, we got 70 ohms there. So that's our control circuit. And then these terminals over here would be our switch circuit. And they should say OL. This one would be our other connection. So this one, if I hook it up, will show low. So that just worked a little better. Let me show you how that relay box is wired up and how I was able to test it on the inside. So if I take out the little whiteboard and I draw the relay box, inside here there's a couple terminals that are my switch terminals. So one end went to a switch contact, almost like a point there. The other one goes to a point here. And then this one can move back and forth. So how do I get that guy to move back and forth? Well, there was two other terminals on this relay box. And these terminals went to a coil of wire on the inside. So across those two, I measured, this is my control circuit, I measured 70 ohms approximately. From these two, because they're not connected, I should measure out of limits, or OL. Okay, but between these two here, I'll change the color again because the picture's getting kind of busy. I should measure, you know, like 0.1 ohms because they're physically connected together. Now, when you put power, if I put 12 volts, positive here, negative here to the control circuit, it would make a magnetic field. It would make a magnetic field in there, and that would pull this contact over, and then I would have power between those two circuits. So anyways, ohms tests are good for like bench testing components, and it can kind of help you figure out how they work. You don't do a lot of ohms tests on the vehicle. It's usually like you're disconnecting stuff because you're taking power from the meter and running it through your parts. Okay, so the most common test you would do would be a voltage test, like measuring your battery voltage or voltage at certain points. And again, remember that I have AC volts and I have DC volts. So I'm going to do something crazy up here. I'm going to actually plug these two wires up into my desk where I have an electrical power strip. So I'm plugging them in right now. And you notice it's measuring 0.6 volts. It's not really measuring any volts at all. Well, why is it not measuring much voltage? Because I have it set to DC. It's looking for DC. It's looking for electricity to go in one direction. I plugged it into my power strip in my garage here, so it's really getting AC voltage applied. So if I push the AC button, boom, it says, oh, gives me a little arrow that says, hey, this is dangerous. And I'm actually measuring 120 volts inside my shop here. Okay, so you can see that there is some danger here. Like you could, let's say you were going to work on the electrical system on your house and you had your meter set to DC and you say, oh, looks like the power's off. I'm not measuring any voltage. If you had your meter set to the wrong setting, there could be a lot of power there and you just don't see it, right? So, you know, I always say when you're dealing with lethal levels of voltage, right, which generally you get around the 40, 50 volt level, you're now in lethal territory. You really need to know what you're doing. So, all right. So we use this meter to measure voltage from our house here. If I had a battery here, I could have measured the voltage coming off that battery. Oh, I got a battery here. There we go. The one thing I'm not demonstrating is how to measure current flow, because when you do current flow, you not only have to go over here to amps, but you have to move the lead over to the amps location. And when you do this, you could very likely blow the fuse in your meter. So it's a little bit more of an advanced test. If anybody is really into like wanting to really use these multimeters and learn how to use them, I'm going to be teaching a class that actually gets you certified on this meter right here in the fall. So anyways, so we're going to stick with volts and ohms today. Remember, amps is the flow measurement. Now, if I want to measure some volts of my battery, I got to make sure that I'm not in AC, I'm in DC. And I'm going to lay my battery right there. Now I'm going to measure his voltage. So he's measuring 1.2852 volts. And this battery is rated at, this AAA battery is rated at 1.5 volts. So yeah, he's getting a little discharged, isn't he? Now look at this. I just hooked it up backwards polarity. And the only thing that happened different is that little negative sign propped up, right? I hook it up right polarity, the negative sign goes away. So one of the things I love about a digital meter is I don't have to worry about polarity as much. On analog meters that had the little needle that moved back and forth, polarity was a big deal. But with the digital meter, I'm just more concerned what the number is, so I don't have to worry about polarity. Now, if I put this on AC, I hook it back to the battery, you'll see that I don't really measure anything because it's looking for alternating current, not direct current, right? So the AC versus DC is a big deal. All right. Now, I got a couple other things up here. Some of this stuff we've talked about before, but I want to talk about it again. It's on the Briggs and Stratton ignition test. It talks a lot about the Briggs and Stratton tool, blah, 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 part number, like 9,330 something. That's this spark tester. You guys have seen it before. I've had it up here in previous classes. The idea with this is you connect this alligator clip to the ground of the engine. You connect this lead in place to the spark plug, and you pull the rope, or you crank over the engine, and you look at the window there, and you should see a spark. What Briggs and Stratton will say over and over is they'll say, hey, don't worry about the color of the spark. Now, ideally, oh, that didn't come out how I thought, but you see what the window looks like, right? So ideally, this little window in the tool, if I draw the tool right here, ideally the spark would be like a nice bright blue spark, but because these ignition systems on small engines, they can't put out a lot of power, a lot of electrical pressure, you might see it kind of look more orangey, and that's okay. What Briggs says is if the spark can jump the gap, you're A-okay. It should be able to fire a spark plug and run the engine if you have a good spark plug in that engine, okay? So they say don't worry about the color. On our car ignition system, we typically say we want a good blue spark because the bluer it is, the hotter it is, the more powerful it is. This Briggs and Stratton part tool 9000 whatever is specially made for small engines. It means that this little gap in here, they've set it to the right distance apart. Do you have to get that one? Oh, no, you don't. In fact, you know what I don't like about this one is this wire is really small and it always wants to, I have like, 30 of these at the school and half of them I had to resolder and fix this wire because it's so small. At the auto parts store, you can get a spark tester like this one. And I like these a lot. They're adjustable, right? But it means you got to know how to adjust them. So I've told you guys this before. If you're testing a small engine, you want a pretty small gap here, kind of right where it says SE, right? Down a little bit below that, and a small engine should be able to fire that gap, okay? This one's got numbers on it. If I unscrew this thing, you'll see a 20, 30, a 40. The idea is that if I have the gap all the way there to set to 20, well, it's going to take 20,000 volts from the ignition system to jump that gap. It would take 40,000 volts to jump this gap, okay? So it's adjustable. If I set this gap up to 20, 30, or 40 and hooked it up to a small engine, it would look like there's no spark because it just can't put out enough electrical pressure to jump that gap. So you'd have to screw it down. But this tester would work really well, and then you could also use it on your car. On your car, I would probably select like a 20,000 volt gap and see if it jumped that gap, and it should look nice, bright, and blue. If I move the gap up to 30 or 40, it might start getting a little bit more orangey red. So it's a great way to test your ignition system and kind of really stress test it. So we tested our coil here with the ohm meter and kind of got mixed results. By testing it with a spark tester, you really will know, can it fire my spark plug or not? Okay. That is an important test. If you get into any troubleshooting, I'll just actually keep the whiteboard up here. If you get into troubleshooting an engine that won't start, right? You got to remember that any engine needs three things to operate, right? It's going to need some heat. Now, where does this heat come from? Well, the heat actually comes from two sources. It comes from our ignition system, right? The spark plug, but it also comes from compression. So use your spark tester, test for spark at the spark, go into the spark plug, make sure you have a good spark plug in the engine, okay? And also we've already kind of went over compression testing and stuff in class. So the heat comes from those two things. The next thing you have to have for your engine, which is usually a given, but not always in a small engine, is air, right? I have to have a good supply of air because we're going to take that air, we're going to compress it. You know, we're going to mix it with fuel. I mean, so if I had a really restricted air filter that's all clogged up, like that could be an issue, right? So to run, we need heat, we need air. We also need some fuel. So heat, fuel, and air, that's what we need to have the engine run. So that means that our fuel delivery system has to work properly, whether we have gas in the gas tank, the carburetor is mixing the right amount of air and fuel together. Those things are both important. So whenever you have an engine that doesn't start, heat, fuel, and air, right? But I'm going to draw one more thing on this screen. I'm going to draw a clock here, I guess an analog clock. All right, 1, 2. And that's time. And that everything has to happen at the right time in the 4-stroke cycle. So I need heat, fuel, and air, but don't forget that I need the spark to happen right at the top of the compression stroke, right? So everything's got to be timed correctly. That also means that my valves in my engine, right? If it's a 4-stroke cycle engine and it has valves, it's a really ugly looking valve, sorry. But my intake valve needs to open at the right time, my exhaust valve. I recently made a video about timing your camshaft to your crankshaft. That sets the timing of the valves properly. Bolting the ignition coil in the right spot would then should make sure that you have your ignition timing correct. But those are important important things. So heat, fuel, and air, and everything has to happen at the right time. Okay. So wrapping that up, if I go back to the computer and I do my other screen share, I'm actually going to get that guy out of the way. So we beat you up with all the electrical stuff, right? What I wanted to say is if you go through chapter 10 on troubleshooting, what you will see is it basically just builds. It just builds everything that we've kind of talked about in class already. It's like taking the ignition and the fuel and the compression and putting those three things together. So they talk about doing some voltage measurements. We just looked at that earlier. They show you some troubleshooting flow charts, right? And this actually is a good chart here, because they say, hey, that you start here. Is the battery charge low? The big question here is, does the engine turn over, right? If I have an engine with an electric starter, remember that electric starting system is just supposed to take the place of me pulling the rope. So if I have a low battery, I'm not going to have enough voltage there to get it to crank over properly. Remember that I got to exceed 250 RPM or so to make spark happen at the spark plug. So here's their flow chart of what to do, testing your cranking system, right? So there's flow charts like this in your service manuals to go over, or trouble charts like you see right here. Like they talk about service life of the engine, right? Again, do a compression test or do a leak down test. That'll let you know what's going on there. And here they're talking about compression and leak down tests, like we've already. So really troubleshooting is just putting all these things together. This is kind of a good tip right here. The fuel flow should be as wide as the inside of the fuel line. If it's not, if just a little tiny trickle is coming out, I have some type of fuel restriction, probably a clogged filter or something in there. So they're testing gravity, fuel flow, but heat, fuel, and air. I mean, that's what it takes. Now, who can tell me what's this thing right here in this picture? Oh, darn it, it's labeled. So I guess if you look at the screen, you got it figured out, right? It is the anti-afterfire solenoid, right? And here's their little quick test of it. They hooked it up to a 9-volt battery. Why? Well, 9 volts isn't 12 volts, but it's enough to make this thing click and move around. So that's a way that you could test that thing. You could also measure its resistance, and you could test the electrical plug with your meter to make sure that you're getting 12 volts to the solenoid, right? All right. So the troubleshooting chapter really just takes the things that we've talked about before and puts them all together. Remember we were talking about governors, and I said, hey, use your hand on the throttle. Well, in this image right here, that's exactly what they're doing there. They're working the throttle by their hand to figure out, is the problem a carburation problem or is it a governor problem? Are they using the choke right? Here's some tests of the needle and seat with the pressure tester, and this actually is a really good one because maybe I have a float that leaks. If I put the float in a thing of water, guess what it should do? It should float, right? It shouldn't sink to the bottom. I shouldn't see bubbles coming out of it. So that's kind of a handy tip. So chapter 10 of your book has some good good tips. Like, they don't really want you, I see people do this all the time, they don't want you to take a screw and just ram it in a fuel line because that breaks up the inside of the fuel line and over time will cause a fuel restriction. But they have some good good service tips, but again, it comes down to heat, fuel, and air. Here they're using that spark tester and checking for spark on the engine. And remember, they say, hey, if it jumps the spark, it's good. Here we see an ignition coil. Is that the advancing style or the non-advancing style? Does anybody know? Remember, you're looking at the gap here. There's no gap. It's got just a little tiny piece of paper in there. So that would be the cheap one, the non-advancing. All right. And it talks about lubrication. And so heat, fuel, and air, that's what you need to make your engine run. And it just kind of is an extension of what we've been talking about, you know, throughout the whole class. I hope that answers some of your questions. Yep, the old one, non-advanced, great. Thank you for answering my question. Any questions, other questions? Let me put up the internet here. If I can, there it is. And let's finish. Let's talk about finishing out our class. So the last test that you're going to be doing is this one on ignition systems. This one right here. And that's going to be due, I want to say, on Wednesday. The big ticket items, like essentially your final exam for the class is taking that engine apart and labeling the parts. There's really no better rubric that I could give you as far as testing you out to see if you can take that thing apart. So that's going to function as your final exam, if you will. And I've killed you throughout the whole class with all these different certifications. So I felt like I tested you enough. Now, some folks have been asking me about extra credit opportunities. You could do this parts lookup for some extra credit points. If you go back to exams, there's more certifications you can do under the intermediate level. And then there's more under the advanced level that you could do for some extra credit points. And if you really want a challenge, you could do the Briggs and Stratton Master Service Technician exams. I have some folks that, you know, they don't want necessarily to take apart an engine all the way, or, well, they can start doing some of this MST stuff. They're difficult. They are not easy. But you know, if you walked into a small engine shop and you said, hey, I got my Briggs and Stratton MST certification, they're going to be like, wow, okay, you're hired. You would still have to be able to fix stuff though, but that'll definitely get you in the door and get you a job. So anyways, so those would be options to get some extra points on Briggs and Stratton. And still, if you do the rest of these activities under the bronze, you can get 30 extra credit points for that as well. So you can do extra certifications and get extra points for that. But really, your big activities are taking apart those engines and labeling the parts, and taking apart the carburetor and labeling that. If you actually put your engine back together and get it running again and document that with pictures or video, heck, I'll give you more points for that, because it's really twice as hard to get it back together as it is to get it apart. So with that, I hope you enjoyed the class. I'm going to keep the discussion, the technical help discussion up. I'm going to keep all that stuff going, and I'll be available to kind of help you guys as you get through, you know, some technical problems. If you're taking a test, you have questions on something. If you're working on something, you can't take something apart. I'm there to help you out. And there might be situations like for the engine that I made a video on. See if I can find that video. I actually had to cut the mower blade attachment off the engine here somewhere. Let's see, where did I cut it apart there? Right there. It might be where you don't want to have to do that. You're like, that's too crazy. I don't want to have to cut that thing off of there. I don't have an angle grinder. Now, I used air. You could get an electric angle grinder from Harbor Freight for like 15 bucks, and you could have done the same thing. I just happen to have an air one there that's a little bit less bulky, but it does the same job. You know, take apart what you can. If you ran into this situation, you couldn't take it apart, well, you can still take the carburetor off. You can loosen up the side cover. You could take some other parts off and label it, and then do some extra credit to make up for some of the other things, or we can get you a different motor. So there's definitely options. This is kind of a worst case scenario with this one in the video, which was part of the reason I picked it. So anyways, remember, if you have questions.
Yeah. So there's no list of things we should definitely be able to find and label, right? Like when I was doing the carburetor, you know, I tried to find what I could, although I had a complicated carburetor that was a shock.
Okay.
Yeah, I had like a diaphragm on top and a slide in the middle, and I was like, I don't know what I'm doing. But I was wondering, like, if there's like a certain things we should find in order to say that we've finished the project.
No, because the circuits in the carburetor vary so much, I couldn't say that every carburetor is supposed to have this. I mean, every carburetor is going to have a Venturi in there, right?
Yeah.
But beyond that, you know, like it could have a diaphragm, or it could have a float bowl on it, right?
Well, I meant for the engine, actually.
It could have a main metering jet that you can get to, or it could not. So that's kind of a tough one. Um,
But I mean, for
what
the engine parts, is there like a, how would we know when we finish diagramming everything whatever we can acknowledge and find?
Yeah, that's a good question. Normally in class, when something's not labeled, I say, well, what's this part over here, right? So if and so this whole thing has been kind of an experiment. Like what I would say is if there's a part, you know, try to find the name of it. And if you can't find the name of it, you can write down, like, I couldn't find the name of this one, and I'll tell you what that is. But the major components, right? Pistons,
Okay.
valves, that, you know, valve springs, rocker arms, if it's got rocker arms. If you can label the major components, that's mission accomplished.
Okay.
Yeah, don't worry about everything on there. Like even on this one, I could have labeled like, here is the magnet in the flywheel assembly, right? And then here's a counterweight to counteract the weight of this magnet, and here's the mower blade attachment, you know. So
Like I label those because those are the things I actually know.
right. Yeah, just go with the main components that you do know, and you'll be good. If there's something, I'll likely tell it to you. But yeah, it's kind of a hard thing, because even with something like the carburetor, I can't tell you that every carb's going to have this and that. A lot of the lawnmower carbs, heck, they don't even have a an idle circuit necessarily in there. So you know, it's not I got to kind of like fudge on some stuff. But I think going
Okay.
through the activities, you know, my wife and I have been talking about this quite a bit. You know, in some ways, I feel like it's been a lot harder to cover information. In other ways, 6 months from now, you guys in this class might remember stuff more because you were on your own having to figure it out. And oftentimes in class, like I'll give people the answer, and then they know what it is right there, but they might not remember what it is a month from now.
Yeah.
So it's kind of an interesting way. But yeah, label everything you can. If there's something like, if you look at the diagrams on the, you know, in your book or on the internet, and you're like, I can't find what this part is, you can always say, I don't know what that is, and put it under like comments or something, and I'll see if I can find out what the answer is for that for you. But you
Okay,
do
thanks.
see different things in different engines. This engine that I chose to do this video on was a flathead engine, where this engine right here, this is an overhead valve engine. So they're set up differently. And so the other one had like a little oil pump thing. This one doesn't even have like an oil slinger on it. It's got this little spike hanging down from the connecting rod that dips in the oil and throws it around. So you'll just see different things in different engines. So not every engine's going to have an oil slinger. Not every engine's going to have a rod dipper like this one does right here. This engine has rocker arms and push rods that I didn't have in my flathead. So it's not easy. Just try to label everything you can, and if you've done that, you're going to get full credit for your activity for sure. So, and if
All
you have
right,
questions
thanks.
on stuff, be sure to ask them, and I'll do my best to answer them. So, all right. Does anybody have any other questions? Well, with that, I appreciate you taking part in the class and in today's Zoom session. I look forward to seeing your engine projects. I've been clicking away at grades, and I finally figured out how to do the comments. Like, I've been doing the grades, but I didn't realize I had to submit the comments. I thought if I made the comment, it automatically did it. And just yesterday or the day before, I figured out you have to click the submit box. And so you should see comments coming up as I've been you know, going through those grades and working on or reviewing your coursework. So I appreciate you taking part of it. Be sure to ask questions if you have them. And you know, we're gonna round this thing out. You'll have this coming weekend to kind of finish things up, and then get everything submitted by next Monday, so I can get your guys' grades completed and posted before the deadline, because we're really close to the start of fall semester. So
Thank
with
you.
that, thank you so much. Take care. I appreciate it. And I hope you learned a lot from the course.
All right.
Take
Thank
care,
you.
everybody.